That is a negative 11 right there, despite the way it might look.
What is the negative 11?
That's 6.67 times 10 to the negative 11. Having trouble reading it?
Yes.
All right, why don't I write it more neatly? So speed is the square root of 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times the mass of the Earth, 5.98 times 10 to the 24th kilogram, divided by twice the radius of the Earth, 12.76. Is that what I had?
Yeah, 12.76 times 10 to the 6.
And that's another one given to us.
That was,
Yeah, I said that it was basically the Earth's radius away from the surface of the Earth,
times 2.
and the radius of the Earth would be something I would give to you.
I got 4.78 to the 23rd, but somebody double check me. To the 20, E to the, E,
That's
wrong.
That can't be right.
Okay, let me try again.
It is traveling faster, much faster than the speed of light.
Okay.
That's 10 to the 6, right, on the bottom?
Yes. See if I can do this without making a full force. Maybe.
Is it, is,
5.59 to the 14th? Or is that still too fast?
It still seems too fast.
Okay, if I'm doing, what am I doing wrong?
Is it 3.827?
I got
Keep
three,
going.
I got 3.125.
No times 10 to those?
Yeah, E
12.
to the 19.
Mine's,
What are we doing wrong?
12.
Did you do the square root?
Yeah.
Oh, no, I didn't.
And you got times 10 to the 12.
Yeah.
So I got 24, just looking at 24. No, none of those are right.
Okay,
I would expect it to be somewhere around 10 to the third or 10.
when you
maybe 10 to
do
the
square
fourth.
root, you're gonna do, when you do square root in the calculator, you do double parentheses in the beginning, right? Because you're like,
Of the whole thing. If you're doing it
Yeah.
all at once, then I would recommend it.
okay, so 6.67.
And this trouble, it's not uncommon, but this is why you need to make sure that you know how to use your calculator.
Will you just look and see what I did wrong? I got like 5,590.
That's
Okay.
what I got too.
Is that right?
That's making more sense.
Okay, but no
The-
E, no to the E.
Well, I mean, it'd be 5.59 times 10 to the third.
What is
But,
that?
yeah, what I was hearing was times 10 to the 14th and 19th and 12th.
Well, that's what I
and
got in the beginning.
things that, if it were true, would
But I put my parentheses right?
get some Nobel Prizes. Pardon?
I put my parentheses right.
Okay,
I
it
think-
seems that 5,591.
Oh, Yeah, 983.
Okay, you got that, you got that?
I did not.
What did you get?
1.56.
Let me see your, let me see what you put. Did you do the square root?
No, I did square root, because I did the first time.
I got.
Oh, I see.
What did you get?
So in the beginning, you're missing a parenthesis, so like, look at
I
mine.
calculated
Double
that.
parentheses.
on the test.
Oh,
See this, try that, try to put a
Practice
parenthesis
right here.
like a double
All right.
place.
I got this.
Why don't we, you got that?
No, I got this.
You got something there very different? I haven't forgotten.
Because you have to do two parentheses.
Why
Because you have
Because
to,
the two.
because, that way you can separate the top from the bottom.
You do the square root.
Because if you do two parentheses in the beginning, it'll separate like the top and the bottom, and then you do two at the end.
Let me do that. That's G, that's mass of the earth. And then you divide it by the orbital radius.
So you don't add one right here.
Square root of that.
So take that one away. You do like two on the top, two in the beginning, and then you do the top numbers, then you divide, and then two at the end, to kind of like close off the whole. So take off that one, and then, yeah, so just one, and then see what that, and then add.
I asked ChatGPT
add one
and they said
more
that
to
too, so I have to
Do the-
do it.
No,
Okay.
the bottom, yeah, cause you're like closing off the whole top.
Look, this is
This is, you see that Y next to the Y? You do that. Oh, yes.
This is my calculator.
Okay.
All right, Jennifer, you getting this down? You still didn't get it. What you got?
Okay.
Let me see your card.
You squared it. You went the wrong direction. Square root. You went. And then you go to 5.
So like you put the two in the beginning and then two at the
I give
end
up.
to close it.
Where were you? 3, 1, 2,
I
5.
got millions.
And you did the square root?
And the moral of the story. Please make sure you show your work. All right, we're gonna take a break here. I'm gonna get a calculator to type that you use on the quiz and get your earbud.
What would the units be?
Oh, yeah, units, we left that off. What would the units be?
What is the 12.76 times 10? That's meters
That's,
per
that is
second.
meters.
Meters per second.
Yeah. We found a speed, so meters per second.
So the 6.38 times 10 to the 6 meters squared,
Yay.
that's what we multiplied by 2 to get the 12.76 times 10 to the
Yes.
6?
6.3
So how
times
is
10 to the
it,
sixth.
how is it just meters? For when you, after you times it by 2?
Yeah, 2 is unitless.
No.
Okay.
You have just 2, you have a length here and then you have.
The length
just,
there.
Same length.
Okay.
So basically, you're adding it to itself.
Okay.
All right. Something that will seem completely different. Momentum. What is the formula for momentum?
MV.
What is the formula for angular momentum? You go back to that first day that we were doing chapter 8, and we talked about the rotational analog.
It's our alpha? Alpha? No.
What's the rotational analog of mass
Oh, mass.
and then velocity?
Inertia?
What did you say?
Inertia?
You didn't read all of it.
Rotational inertia?
Okay. Or moment of inertia.
Moment.
All right, so we got capital I, and then
I just have capital Y, I don't know why.
Capital I, that's moment of inertia or rotational inertia. That's the symbol.
Mhm.
And then for
Oh,
velocity,
omega.
all right, so we have another formula here. We talked about doubling up, this is one of them. So angular momentum deals with, well, taking into how the mass is distributed, that's in the I, and how rapidly it's rotating. So if I take a rod, rotating about its center, rotating about its center,
You said how mass is distributed and
and it's basically angular velocity, how fast is it rotating?
how fast?
So rod rotating about its center. We'll do mass of rod, 2 kilograms, length of rod. Say 3 meters long. So, well, basically a rod running from the ground to roughly the ceiling there, rotating about its center. And let's say it rotates at 4 RPMs.
What's the
What-
symbol in front of rod? Is that an I?
Look here,
Yeah.
L,
L.
it's the length of the rod.
Okay.
It rotates at 4 RPM, in other words, revolutions per minute. What is its angular momentum? And when I say rotating about its center, there are actually several different ways that can be interpreted, but oh, we have a rod here. Rotating about its center like this. Except spinning all the way around. But if I tried that, something quite possibly would break.
Is that for ppm?
RPM, revolutions per minute. Think back to all the vinyl albums that you own.
Always listen to.
How many of you own vinyl albums? Anyone left?
You said
Besides
what?
me?
Vinyls.
You got some? Excellent.
I have CDs. They rotate.
They do. I don't know what the angular speed of this is.
Those-
The big albums are 33 RPMs. The what are generally called 45s because they 45 RPMs. And then there's 16 RPMs if you go old enough. And 78s. All right, so let's take it piece by piece. I'm trying to find angular momentum, so I need to figure out what the moment of inertia is, and I need to figure out omega. I didn't give a direction here, so we're gonna have to be directionless. But the moment of inertia of a rod about its center, and for this, I'm not expecting you to know it, but it was page 130 something. There we go, page 138. Stick about its center, 1/12 mL squared. This L is the length of it, not the angular momentum. And so I'm just gonna put a lowercase l here. So match what it did down there. And so it's just straight up plug and chug. I have 1/12 times a mass of 2 kilograms times a length of 3 meters squared.
Yeah.
Units.
Kilogram meter square.
Now, this number by itself doesn't really tell us much, but it's how it's applied that matters. All right, so now omega. I want to put this into some nice units here. I have revolutions per minute Yeah, we could stick that in there, and so the magnitude of my angular momentum would be 1.5 kilogram meters squared times 4 revolutions per minute. At least the math I can handle, that's 6. What would the units be? These are non-traditional units we're working with here, so it's not like you can go, oh, angular momentum, here are the units. You have to look at it based upon the equation.
Kilogram meters squared revolutions per minute.
Which is sort of a mess. It is a correct answer. Those are not SI units, it's not international standard. So let's put it into international standard. A revolution, that's around the circle once. It is basically an angle. So if I go around the circle once, how many radians is that?
Wasn't that like 7 or something?
It's a little more than 6, so you were close, but we can be more precise than that. How many radians in a circle?
Radians.
Yeah, 400 radians.
2 pi radians.
Yeah, 2 pi. So 6.28, slightly better. So I take my 4 revolutions per minute. And a revolution, that's once around, is 2 pi radians. So that is, so multiply by 2 pi radians per revolution. Revolutions would cancel out, and what I'm left with is 8 pi radians per minute. Now, 8 pi, at some point, we'll use a calculator to get a more precise number than that. And then minutes isn't SI. What is the SI time unit? The International Standard Time Unit.
Seconds.
Yes. And how many seconds in a minute?
60.
So times, seconds at the bottom, 60 seconds over a minute. And so whatever 8 pi over 60 is radians per second. Now, this is a typical way of doing conversion. There are other ways. I'm going to do a slightly different way of doing the exact same thing. I know that 1 revolution is equal to 2 pi radians. I know that 60 seconds equals 1 minute. So what I'm going to do, instead of writing it out like that, I'm just going to replace the units here. So that 4 revolutions becomes 4 times 2 pi radians, because that's a revolution. And a minute, that's 60 seconds. So there's the math problem right there, 4 times 2 pi divided by 60, which is in essence what we have right over there. And what is that?
The
8 pi divided by 60.
it's 0.4188.
Units?
Rad seconds. No.
Sound like a-
Rad per second.
There we go. So now we can get standard units over there. So the magnitude of my angular momentum is going to be 1.5 kilogram meters squared times 0.4188 radians per second. And we end up with something magical.
0.6282.
One more time.
0.6282.
And then the units.
kilogram meters square rad per second.
Aren't those units so much nicer than the pesky kilogram meter squared revolutions per minute? All right, the one advantage that you have converting it, one, it's a standard unit. So if we have to use this for something else, we don't have to worry about conversions at that point. But also, radians is something that you put in when it's convenient and you take out when it's convenient. So you actually could just write kilogram meter squared per second. There is not a single word unit for it. Like with regular momentum, they just haven't gotten around to doing it yet. So that's how you find angular momentum. Now, just like with regular momentum, in a closed system, it is conserved. Which means that my total initial angular momentum total equals my total final. And now we shall see if I throw one. Let's see. This one, I'm not gonna smack my hand on anything. Any of you know the Epley maneuver for vertigo? All right, if this goes badly, I might ask you to look it up and perform it. It seems to be more effective than the other ridiculous thing when I try to do it myself.